Oh, is the video on?
Yeah.
Okay, thank you. And what I want to study the anti-commutation relation is this weird new kind of number called Grassmann numbers. And that was something you have to get used to. But nonetheless, this is the way you can describe fermions. And one of the things I will be asking you to do in a homework is that when you have this angular Hamiltonian, we can know the kinetic potential and go to the momentum space. Then these C's satisfy also canonical commutation relation. But this actually is in the bulk normalization, so I forgot to make this factor. The system is now, in this case, living in a finite size box with periodic boundary condition. And each momentum mode satisfied is anti-commutation relations for fermionic harmonic oscillator. So that's something you can do. And then if you actually replace this using this momentum modes, this Hamiltonian would turn into sum over all the momentum modes. And for each mode, you have this Hamiltonian that's very easy to understand. Namely that depending on how many particles you put into the momentum mode, you get the energy of p squared 2m minus mu. And then we could find the ground state for this. And that ground state turned out to have this Fermi C. This is the occupation number for each momentum mode. That's 1 all the way up to the Fermi momentum Pf, which corresponds to square root of 2m times capital potential. And then you don't put any particles in there for the momentum modes above the Fermi momentum. So this is the ground state. And already at this stage, this system shows very interesting property of having this degeneracy pressure. Because the fermions resist against overlapping with each other at the same location, because they can occupy the same position eigenstate or same momentum eigenstates. So if you try to squeeze this system, then there's a resistance for it. That's nothing but the pressure, and that pressure is called degeneracy pressure. So there are many words that came out with this. So this kind of system, first of all, is called the Fermi gas. You occupy all the states up to Fermi energy. Corresponding momentum is the Fermi momentum. Anyway, we have to emphasize that everything below the Fermi energy is occupied. Sometimes you want to be a little bit more explicit. And then you say this is a Fermi degenerate gas, and it means exactly the same thing. But the fact that you put all the states precisely with occupation number 1 up to Fermi energy, you say that's actually Fermi degeneracy, and you say Fermi degenerate gas, and hence its pressure is called degeneracy pressure. Yes?
So since Paul's exclusion principle is responsible for the degeneracy pressure, why don't we consider it as a fundamental force of nature that acts only on fermions at low scales?
Because this pressure arises even when there's no interaction among particles. So each fermion is totally free here. There's no interaction that looks like we talked about before, we're not putting that in. But still, we have a pressure.
Yeah, but pressure, I mean, intuitively arises because of some interaction between the
No,
particles.
no, it's not an interaction. It's really the fact that two fermions cannot occupy the same state. That is enough.
And there's no
to
deeper
provide this.
understanding of that?
No, this is the understanding. So you can actually do a more precise calculation if you like. So if you have this Fermi degenerate gas in this finite size box, summing over the momentum modes in the limit where you take the box to be large is given by this integral. And I think I explained this to you before, but let me just remind you, when you put the system into a finite size box with a periodic boundary condition, then momentum has to be quantized in the unit of 2 pi h over L, such that e to the I p x over h bar is periodic. So when you go by length L in x direction, you're looking at a pxL over h bar. Px is 2 pi h bar L times nx, times L cancels this n. Then you have exponent 2 pi h bar nx over h bar, that's 2 pi nx. So as long as these n's are integers, then that satisfies the periodic boundary condition. That's why the momenta are quantized. But when you sum over all the momentum modes, which is basically meant to be sum over all integers, then you can put in this factor without changing anything. So I factor L cube out. And 1 over L cube is basically the interval in each direction. If I further put 2 pi h bar, right? Sorry, I'm doing the other way around. Huh? Sorry, I get it. Upstairs and downstairs somehow not compatible with each other. What am I doing wrong here? 2 pi h bar cube. I factor this one out. I put this one in. So again, I haven't changed anything. But the point here is that 2 pi h bar over L corresponds to this unit of the quantized momentum. So summing over all n's basically comes with this mesh of 2 pi h bar over L intervals. So this sum, in the limit where L goes to infinity, becomes infinitely close to each other, and then it reduces to the integral. But integral over momentum, of course, has the unit, which needs to be compensated by this interval momentum space. So this sum turns out to be same as momentum integral times this interval. So that's why when I actually keep this one in and keep this one out, this sum reduces this momentum integral d cube p, because this one cancels this factor over here. And this factor I took outside remains. So the end result is that sum over all momentum modes can be reduced to this integral. And this integral is called the phase space integral. Because the phase space is meant to be a space made of x and p in classical mechanics. L cube is nothing but dx, d cube x. So the rule of thumb is that whenever you have the Hilbert space, you can replace sum over the states in terms of phase space integral, dx dp, which has a unit of h bar. You divide it by 2 pi h bar to find a cell in position in momentum space with an area of 2 pi h bar. And then you divide the phase space in x and p in terms of these cells, each occupying the area of 2 pi h bar. This corresponds to some of the quantum states. And we're dealing with 3 dimensions, so I have 3 powers of these. And then the unit area now becomes the unit volume of the 6-dimensional hypercube in 3 dimensions of x and 3 dimensions of p. So this is a standard technique in StatMech. If you haven't taken StatMech class, you may not have seen this before, but this is actually a very good rule of thumb to remember. So namely that whenever you have a phase space, then you divide the phase space in the unit of 2 pi h bar to count the number of quantum states. And knowing this, and this is in the lecture notes, I hope you can look at it later. Knowing this, you can work out the number of particles in the system by occupying all the momentum moves up to Fermi momentum. Then taking this as a cube in momentum space, this is 4 pi pm cube over 3. Right, it's the volume of a cube. On the other hand, the total kinetic energy in the system, again, this is meant to be sum over all states. But for each state, kinetic energy is p squared 2m. So you integrate this one instead. Then this becomes 1. So this part is the same. You have 1 over 2m. And the rest is p5. And the same 4 pi 1 over 5. Right? So this is the energy in the system. So in thermophysics language, this is the internal energy U. So what you're supposed to do is that inside this volume, you have n particles in it. Then you ask the question, what happens to the energy when you change the volume of the system infinitesimally? And then du is minus p dv, so that's how you can compute the pressure. Yes?
Shouldn't it be L cube?
Sorry?
L cube.
L cube. Ah, thank you, thank you. Yes, this is L cube, L cube, L cube. Is that it?
Yes.
Yeah, thank you so much for pointing out my mistake. So the idea is that when you have U expressed in terms of Pf, Fermi momentum, and you change the volume, and to ask the question how much energy changes, by keeping the number of particles fixed. So you have to work out how you are supposed to change Pf when you change L. And under that condition, you look at how much U changes. And because we have to keep n constant, you can see that LPF has to be held constant. Then you look at the expression L cube PF cube. This is LPF cube times PF squared. This is held constant, but this has to be kept as 1 over L squared to maintain the same number of particles in the system. So then you see that the energy goes down like 1 over L squared. So U is proportional to L minus 2, which is the volume to minus 2/3 power. Then you see that du is minus 2/3 dV and proportional to. Then this piece here, I didn't work out the coefficients, it is what corresponds to pressure. So that's how you can actually work out what pressure should be if you actually put in all these constants into the calculation. So this is actually great because what physics does for you is that when you have a system of just free particles, you can compute the pressure of the system from the fundamental principle, and you find that pressure is non-zero and positive as expected, even when you don't include any interruptions in the system. So that's how you actually work out the equation of state for ideal gas. And in this case, it's not the usual ideal gas because of this strange power law, but nonetheless, you apply the same idea. What is it called? Kinetic theory of gas. The same idea. All you have to do is just make sure that you sum over these quantum states properly up to Fermi momentum, and that would allow you to compute the pressure of the Fermi degenerate gas exactly on the fundamental principle. Yes?
So how are we assuming that 2 pi h bar is the smallest unit of phase space?
That goes back to that argument. So in the finite volume, you know exactly how you sum over the quantum states by summing over these integers. But when L is large, the large enough box, that interval in this sum becomes so tiny so that this discrete sum can be replaced by continuous integral. And because they have momentum space comes in the interval 2 pi h bar L, you know exactly how you convert this finite sum into the integral. That's a definition you learn about integrals, right? You start with some discrete sum, you take the limit of infinitesimal intervals, that's how you define the integral. So that's what I'm doing right here. Then you know exactly how the volume has to be normalized in the unit of 2 pi h bar. So there's no ambiguity in this discussion. Any questions about this? Okay, so that's how we know that the Fermi degenerate gas has a finite pressure, even when you don't include any interactions among fermions. Just the fact that they hate each other, they don't want to come close to each other, they want a social distance among themselves, I guess. And that already gives you this finite pressure of the Fermi degenerate gas. Then I told you that this is actually a way the star can be supported against the gravitational pull. When the star runs out of fuel, it doesn't create energy anymore, so the gravity only pulls. But once this is actually a Fermi degenerate gas of electron, there is a pressure, as we just talked about, to resist the gas to be compressed any further. And if they balance against each other, then you have a stable system. That is a system called white dwarfs. And our sun is on the path of becoming white dwarf at the end of the day. And it's not producing any energy anymore, so all the energy white dwarf can release is sort of slow contraction from originally big star, now becoming a much more compact star. And it releases energy for a while, but it's not really producing energy on its own, so it basically sort of eventually fizzles to no light and becomes completely dark at the end of the day. So that's the fate of a sun at the end of the day. And then I told you that you can actually estimate the mass of the white dwarfs just by equating this total kinetic energy, U in the system, to its gravitational energy. And then you can find that the mass turns out to be of the order of the solar mass. And I think I wrote down the expression for it. Oh, I didn't print that page because I was done with that discussion. Or maybe, yeah. Then the mass, based on some back of envelope estimate, turns out this expression you wrote this down on your notes already, so you don't need to do it again. So you do get an estimate of the mass of the white dwarf, which is surprisingly close to the mass of the sun itself. So this is a way you can basically get the mass of the sun out of the fundamental constants like h bar c, Newton constant, and the mass of the proton. So that's what the end of the discussion I had on Wednesday. Any questions about what we have done? Okay, so I guess this part of the discussion is the only thing I'm adding new today. But now I'd like to come back to this Hamiltonian. So as we just talked about, this Hamiltonian is the ground state. I write the same thing again, which corresponds to this situation, namely that this ground state is not a vacuum state because we have particles in the system. This ground state is annihilated by the annihilation operator when P is above the Fermi momentum. But this state has K states occupied, so the condition is actually backwards, namely that you cannot add more particles to the ground state when the momentum is less than Fermi momentum. So this is the definition of the ground state. But just like what we talked about in the case of Bose-Einstein condensate, we would like to also understand not just the ground state, but the microscopic excitations on top of it. And when we start talking about excitations, this description is not very convenient. Because when you create excitations, you are creating something. So I'd rather use creation operator consistently to understand excitations. But using this ground state, what I have to do is to think about excitation, is that when I add one particle here, that would correspond to creating particle on top of the ground state, which is good because I'm creating something. But another possible excitation is that I remove a particle from the ground state. Because the energy of this momentum mode, when P square 2m is less than chemical Fermi energy mu, is negative. So by removing an electron of this momentum mode, I'm removing negative energy, which means I'm raising the energy by the negative of this combination. So removing electron out of the ground state turns out to create excitation to the system. And if you think about removing one here and creating one there, which is nothing but the moving electron from one momentum mode to this momentum mode, then increase in kinetic energy can be very small. It can be infinitesimal. But at least you can see that going from here to there increases the energy of the system. That's why this is an excitation. But this excitation is a combination of removing momentum mode with negative energy here and adding an electron with a positive energy over here. So I have to use two different languages depending on whether your momentum is less than Fermi momentum or above the Fermi momentum. And that's kind of inconvenient. So instead of talking about this, idea called hole that removing electron is the same thing as creating a hole. It's all filled up to the Fermi energy. Removing it is actually creating a hole. And if you put it that way, the hole creates an excitation, increases the energy, so the hole has positive energy. So this energy increases, while for the electron, energy decreases. So treat all the momentum modes consistently in the same fashion to talk about excitation of the system. It's much better to talk about the hole instead. So what you do is the following trick. This is the anti-commutation relation. But if I define new creation relation operators, where this I define to be D minus Q, this I define to be D minus P. This is the same as delta PQ. And because P and Q can be any of the momentum modes, I can consider this negative P to be, let's say, L, this negative Q to be L, and this is delta minus K minus L, and that's 1 when K and minus K and minus L are equal, which is the same thing as when K and L are equal. So I can now obtain this anti-commutation relation. But the anti-commutation relation is the sum of operators with two different orders, with a relative plus sign in between. So even if I interchange the order, doesn't change, unlike commutators. So what you find here is that this new D operator satisfies the same anti-commutation relation, where D of L is an annihilation operator of the whole, which corresponds to the creation operator of the electron. D dagger of K is the creation operator of whole, which is the same thing as annihilation operator of electron. So this is just a purely mathematical trick. But if you actually do it this way, C of P is an operator remove electron that increases the energy. But instead of using this annihilation operator for the electron, I can use this instead, a creation operator of whole. Once again, that increases the energy. Then I can consistently use creation operator for all momentum modes in a way of increasing the energy and hence creating the excitation. So the idea is that by using this mathematical trick, I define D of P to be same as the original relation operator when P is bigger than PF, but use the creation operator instead of momentum minus P when P is less than PF. And correspondingly, creation operator is just count the Hermitian conjugate of the whole thing, of both of them. And when we define this D and D dagger, what used to be term of the Hamiltonian is now rewritten by C of P is D of minus P. C of P is D dagger of minus P. And now you need to remember that they satisfy anti-commutation relations. So if I rewrite this in the opposite order, because they anti-commute, this plus that one is minus plus it, 1 plus 1, which means I have to put minus sign here. Again, these are anti-commuting objects, plus 1. And minus mu, I forgot. And because of this minus sign, if I write this now as d dagger minus p, d minus p, in the usual order of the annihilation creation operators for harmonic oscillator, you have to switch the sign of taking in parentheses. And then this combination is positive for the most below the Fermi momentum. And this looks more normal, namely that when you have this Hamiltonian written with a number operator, the coefficient of the number operator is now positive. So at the end of the day, the Hamiltonian now looks like this. So whenever you're not talking about the most above the Fermi momentum, D and C are the same thing, doesn't change anything. P squared 2m minus mu was positive already from the beginning. Its absolute value is the same. I haven't changed anything. But when the momentum is less than Fermi momentum, original Hamiltonian has this negative coefficient. But by rewriting the original electron creation relation operator, using this creation operator of the whole, I managed to switch the sign here. This is now positive, which is nothing but absolute value of p squared 2m minus mu. Then this Hamiltonian looks much more easy to deal with, because whenever you act d dagger on the state, you always increase the energy. Definition of the ground state also becomes simple, because this is what I need. When momentum is less than Fermi momentum, C dagger P is the annihilation operator of the whole, D of minus P. So acting D on the ground state, it vanishes no matter whether the momentum is above or below the Fermi momentum. Again, that's a very consistent way of treating all momentum modes. So writing Hamiltonian this way, this thing is always positive. Creation operator always increases the energy. That kind of makes sense. And your ground state is obtained just by declaring that it is annihilated by all annihilation operators for every momentum. So this is the idea called whole. So all we have done is use this mathematical trick. An anti-commutator doesn't depend on which way you write it. So you relabel what used to be the creation operator by annihilation operator, what used to be annihilation operator by a creation operator. So when you actually create a hole here, same thing as removing an electron, that raises the energy. So you're calling this instead as the creation of a hole. And that's the physical meaning of this mathematical trick. Once you do so, your ground state is now very simple. You don't need to specify two conditions. You specify only one condition instead. Instead, it's annihilated by all annihilation operators. And your Hamiltonian also looks simple because it's a number operator times the positive coefficient. That's something we are used to. So this is the way we can understand or describe Fermi degenerate gas with this idea of new creation operator or annihilation operator. Yes?
So in the creation of the, just to make sure, in the creation of the whole picture, we are creating a new hole, but not removing the electron with the momentum.
Right, so this creation operator of the hole is just removing this electron.
Is it
So that's the same thing as the creation operator acting on the ground state.
But it's creating the hole, but how is it removing the electron? It's not removing the electron.
because the definition of the creation operator of hole is really the relation operator for the electron. They are the same. That's how I define this new operator D.
I see, okay.
Yes?
And why is the minus sign?
Yeah, so that's something I haven't explained yet. Thank you for asking that question. So electron here has momentum P. And if I remove this electron, your system now has lost momentum P. So to understand this in terms of the hole, you have to say you are adding a hole with the momentum minus P, so that after adding the hole, you lose momentum P, which was supposed to be the same thing as removing electron of momentum P, so the system indeed does lose momentum P. So when you label creation annihilation operator for hole, you have to invert all the quantum numbers. You are removing momentum P, so the hole carries momentum minus P. In addition, you are removing the charge minus E of the electron, so the hole carries charge plus E instead. The hole is actually a positively charged object. So you switch all the quantum numbers between particle and a hole, and that's how you can define the hole with negative momentum P and charge opposite from the electron, which is positive P. Thank you for asking the question. Yes, over there.
So why don't we use this thing with holes, like even in classical mechanics? So for example, if I was in a room and I got some like kinetic energy and you took me out of the room, the system would have my energy outside and the negative energy here. So why don't you describe, for example, in quantum mechanics, the energy of the room as like infinitely many negative energies of my own?
I think you could, but the main difference between classical and quantum mechanics here is this condition of Pauli exclusion principle, which I claim is a diversity principle. You cannot occupy the same state more than once. In classical mechanics, there's notion of a state. And there's no condition that you cannot put more than one particle into that state. So the idea of hole works only because you have well-defined situation where the state is already filled. Because you cannot add any more, all you can do is to remove one, and that's the idea of the hole. But in classical mechanics, this condition is not that rigid. So I suppose you could use it, but it's probably not very useful. Yes?
So, just extending that analogy, does that mean that the hole has negative mass?
No, the mass is still positive. So let me talk about this. So now that I have the Hamiltonian, you can plot the energy as a function of momentum. Initially, the energy for that state was p squared 2m minus mu. So it looks like this. And this is the Fermi momentum, right? But now that there's an absolute value on this combination, I flip this. So this is the excitation energy spectrum, which is always positive now. This is gone. And in particular, at the Fermi momentum, excitation energy vanishes. So in this case, you say the system is gapless. Gap is the word for the energy, which is the minimum value to create excitation. And for this excitation energy, which is absolute value of 2 p squared over 2m over minus mu, the minimum energy can be 0, and therefore gap is 0. which means the system is gapless. And whether a system has a gap or not is actually a very important property of any condensed matter systems, because if you go to very, very low temperature, every excitation is suppressed by Boltzmann suppression factor, e to the minus beta E. But in this case, E can be infinitesimal, which means that no matter how low temperature you go, you can still create some excitations for the system. On the other hand, when the system has a gap, and you start cooling the system below a certain temperature, your state becomes totally rigid. You no longer create any excitations, whatever. They're all Boltzmann suppressed. So in some sense, the system with no gap, the gapless system is kind of soft. You can keep creating some level of excitations no matter how low temperature you go. But when the system has a gap, below a certain temperature, you cannot create any excitations anymore. The system kind of solidifies. It's kind of hard and rigid. And so it really changes the property of the system depending on whether you have a gap or not. So this is actually a very important question, whether a system has a gap. But anyway, I hope this point is clear. And to answer your question now, excitation energy is always positive, but can be zero. On the other hand, when you actually see what happens when you apply the electric field, if you're thinking about the electron, then the MA of the electron is E. If you have a hole, electron moves this way because the charge is negative, hole would move this way. But what you see here is that this is the force on the electron, this is the force on the hole. But for a given force, this M is still positive. So the mass is still positive. So you change all the properties of between electron and a hole, but mass is the same between electron and a hole because it has the same inertia. Hole would have the same inertia than electron, and hence the mass is the same. Does that answer your question?
But then how are the two pictures the same? Because in the annihilation picture of the electron, you're reducing your mass, but in the creation picture of the hole, your mass stays the same of the system.
So see, what I mean by mass is actually the inertial mass. So inertial mass is the same. That's what I'm saying. I think you're talking about different kind of mass here. So what is the definition of the mass you're talking
in the
about?
annihilation picture of the electron, when the electron is removed, the system's mass also reduces by the amount which is the electron's mass, right?
Ah.
But when you're creating the hole, since the mass remains the same, the total system's mass is still the same.
Yeah, that's true. So that actually has to do with this constant term plus 1 here. So this is plus, so this is plus 1. So you do lose energy indeed after relabeling everything in terms of the force.
I see.
But this is constant term. So as long as you're talking about just the excitation of the system, you can forget about the constant term because you're using this operator to create microscopic excitations or you're moving microscopic excitations. So at the end of the day, the constant term doesn't matter. But if you want to be careful about everything, then you have to keep the constant term in, which describes that you do have energy in the system originally with the electron. But to create an excitation, then after doing this rewriting, after the writing you can forget about the constant term because that's the system of the ground state. And then you can talk about excitations without remembering what the energy of the ground state was, as long as the only interest is in excitation of the system. Does that answer your question?
Yeah, but
okay,
so is the hole identical to a positron then? Because it's
that's what I will get to later on. So when we get to the relativistic quantum field theory in the second half of the class after midterm, then we start writing down the theory for the spin 1/2 electron consistent with the relativity. And that has to do with what is called the Dirac theory. Dirac theory looks like there is a state with negative energy. But if we have a negative energy state, you are better off filling that state to lower the energy of the system. So the ground state should have all the negative energy state already filled. And that's precisely that kind of situation. So your ground state has all the negative energy states already filled. So the spectrum looks a little bit different from the case of like a piece of metal, because your state now looks like this. Because it's relativity, energy starts out the mc squared. That's the positive energy state, and you don't fill them. But you also have negative energy states as a function of momentum, and you need to fill them to define the ground state. And there is a gap in this case, so this system is not gapless. But the idea is the same. To create an excitation, you create a hole here, and hole has the opposite charge from the electron, so the charge is positive. And once you create a hole here, that would increase the energy more than mc squared. And that is actually, as you said, is a positron. So here, you can create an electron. Creating a hole here turns out to be antimatter, positron. And that's how the prediction for the existence of antimatter emerged from the relativistic QFT, which was discovered by Anderson and Caltech in cosmic rays. Antiproton was first discovered on the Hill by the Bevatron. And that's how we know now that antimatter does exist for every particle species in the universe. So the idea of the positron or antimatter in general is basically exactly the same thing as what we're talking about the hole over here. So that's how non-relativistic QFT for the quantum matter system and the relativistic QFT for particle physics are actually very much related to each other. And that's another thing, that's the beauty of QFT. It's such a versatile language. It can be applied to many different systems. And the same concept will carry over from one system to another. And this concept of the hole carries over from piece of metal to the theory of the universe of matter and antimatter. And so that's the connection, which is actually very interesting. So you're completely right about that. Any questions? Yes?
You said the operator over there, a piecewise operator. It's like when the momentum is beyond the Fermi momentum, you should restore the D into the original C. I just want to make sure whether the D over there is a piecewise operator, because when the momentum is below the Fermi momentum, you are changing the original C into a D, and
right.
then so it's a piecewise.
Piecewise in the sense that when P is less than Fermi momentum, we're referring to the pole. When the momentum is above the Fermi momentum, we're referring to the electron. Is that what you mean?
Yeah.
Yeah, that's right, yeah.
Okay, thanks.
But that makes it the ground state defined much simpler. That makes the Hamiltonian look simpler. And so this is the way which is much easier to deal with when we talk about the excitation of the system. Thank you for that question. Any other questions? Okay, I hope this idea makes sense. Yes, Kay.
Question. So we talk about the idea of having the annihilation operator and creation operator in whole.
Right.
But actually, we saw whole in semiconductors as well.
Right.
So this is not exactly just a hypothetical mathematical.
That's right, yeah. So when you have a semiconductor, and you have p-type and n-type superconductors, and n-type superconductors have basically more electrons than you need, so you tend to have electrons floating around, and then they would flow in the electric field. In p-type superconductors, you dope the material, which has fewer number of electrons in the atom, so you have a deficit of electrons. Then you say that's a system with a bunch of holes. So when you apply electric field on the system, then electrical current would flow in the opposite direction from n-type superconductor. So that's exactly right. So that's how we use the language of hole for practical purposes to study things like semiconductors.
But now the question will be, is this whole hole the same as the hole that I'm taught, that we can observe in?
Yeah, it is.
Okay.
So the idea is that when you have, let's say, germanium, and when you actually replace some of the germanium by, I think, arsenide, that's the next to germanium, if I remember correctly, then this one has basically one extra electron compared to germanium. Of course, nuclear is different, but we are only looking at the property of the electron in the system. So as far as the electron goes, that's basically adding one electron to germanium. So compared to pure germanium, this system has additional electrons in it, and these electrons would move when you apply electric field, and that will lead to electric current. So that's the N type, because the charge carrier is negative. But when you replace germanium by, what is the atom here? One before germanium, does anybody know? Anybody good with the chemistry class? Nobody? Okay, so you go.
I don't know how to spell germanium.
Oh, no, look up periodic table.
Okay. Oh,
It's gallium.
Gallium, okay, thank you. So for the purpose of electron properties, gallium is germanium minus electron. So you have fewer electrons in the system, and you say this is the same thing as adding a hole. And that's the p-type p-type the semiconductor, the positive charge carrier. So when you apply electric field, here electrons move this way, here four holes move that way. So you have the opposite charge carriers in the system. And these holes are nothing but these holes. And to make it a little bit clearer, when you talk about not even the contrast balance system, but just an atom. Suppose you have an argon atom, which has 2 electrons in one s orbital and 8 electrons in one s and 1p and 2p orbitals. 1, 2, 3, 4, 5, 6, 7, 8. No, this is neon. What? No, argon, right? Oh, neon, that's right, neon. So this is the closed shell atom, which is of course very stable, very inert chemically, and so on and so forth. And when you add one more electron on top of it, I think that's sodium. And this is adding one electron in 1, 2, 3 s orbital. And you know this is an alkali atom, it's very chemically active. But instead, you can think of fluorine as removing an electron from alkyl. Then you can describe this as a hole in 2p state. And this is actually a much easier way to figure out, for example, quantum number of fluorine. And if you look at the energy levels, you have 1s, 2s, you have 2p, but 2p actually comes in 2 different orbitals, because you're adding orbital angular momentum 1 and spin angular momentum 1/2. That will give you total angular momentum of either 1/2 or 3/2. 1/2 is lower, 3/2 is higher. So you start filling these states and then eventually get to this state. And fluorine has one electron removed from here, so immediately you can tell that fluorine has a ground state of spin 3/2, because you are removing electron or adding a hole in 2p 3/2 state. So using the language of Hall, this is not condensed matter system, this is pure single atom. But already here, using the language of Hall is useful because you can figure out the quantum number of the system much more easily than trying to combine the wave function of this remaining 9 electrons and write down multiple wave function. So concept of Hall is very universal, works in condensed matter systems, it works in the atoms, it works in particle physics. So whenever you have fermions, which correspond to sort of filling up to energies, which correspond to the closed shell atom, then idea of the Hall is actually very useful. And when you ask the question, what is the quantum number of, let's say, oxygen, then once again, trying to build a wave function of oxygen requires the 8-body wave function, which is kind of complicated. But if you think about removing 2 holes, electrons, namely creating 2 holes into the system, then you know the quantum number 1 hole. Putting 2 holes together is sort of simple. You probably have done that in quantum mechanics class. That's how you know that oxygen has actually an overall spin. And if you actually cool the system, the oxygen, and then you actually go for gas or liquid. Liquid oxygen is a magnetized fluid. It has all kinds of weird properties because it has spin in it. And so the fact that oxygen does have a spin is just simple the addition of angular momentum of 2 p3½ states. And that's something you can understand much easier by using the language of the Hall. And so, once again, the Hall is actually a practically useful concept. So in the condensed matter systems, like a piece of metal, then you can talk about this Hall as a carrier of positive electric charge. In the case of semiconductors, that's indeed the language you use, which is the best way of describing a piece of semiconductor. If you're talking about also these multi-electron atoms, going from the closed shell atoms, you can add electrons to describe slightly bigger atoms, or you can add holes instead to talk about slightly smaller atoms. Then it's a lot easier to figure out their properties by using the language of Hall when you're close to closed shell atoms. Yes?
So is a hole a fermion or a boson?
Fermion, because the Hall is also anti-commute. And where did it go? It's gone now. So remember, we define annihilation operator of the Hall to the creation operator with the opposite momentum. And when you look at anti-commutation relation, this is 0, just because they are both creation operators of fermion. The fact that 2 annihilation operators anti-commute means the Hall is also a fermion.
But that doesn't make sense, right? Because we could imagine removing all electrons from our system, and that would be identical to creating as many holes as there were electrons before. And so we would have a Fermi gas again, a Fermi degenerate
You
gas
can say that,
again.
yeah. But again,
But now we have nothing.
you can create hole only once, because creating a hole is the same thing as removing an electron.
Yeah.
Once you have removed the electron already, you can't remove it anymore,
Yeah.
which means that you cannot occupy same hole twice.
Yeah. So, but if we think about the picture where we are removing electrons, then once we are done with removing all electrons, there's nothing left, right?
Right.
But if we are putting holes instead, then we are left with a Fermi degenerate gas in the end.
Yeah, so you can say that removing all of these electrons is the Fermi degenerate gas of holes. You could say that.
And that is equivalent to nothing.
Yeah, that's right.
Okay.
And of course, once you have Avogadro number of holes, that's another complicated system to deal with. So it's not a very useful or pragmatic description of the system anymore. But mathematically, you can do that.
So that means that vacuum itself is a Fermi degenerate system.
Yeah, so the way we actually talk about this, the particle antiparticle in Dirac theory, is that you have this spectrum, you fill all of them. So what it means is that our vacuum, an empty space, is filled with negative energy electrons, which is called Degeneracy. The same way that we talked about Fermi. And that's a weird idea. And because you're filling all these negative energy states, 0-point energy is actually negative instead of positive. And then the question is whether it is physical, is something you can measure. The answer is we don't know. We don't know how to measure 0-point energy, even for simple harmonic oscillator. So whether this actually is physically important fact of having this negative energy of Degeneracy is an interesting question. And if you figure out how to measure that, that's great. But I don't know. So, but nonetheless, the idea is the same. Empty space is filled with this negative energy electrons. That's the idea of the Dirac theory.
So then that means we can't compress empty space beyond a particular value, right? So there is a characteristic length scale.
Yeah, so it turns out that because you have this Degeneracy, you can talk about excitation of taking one electron to over there. And that's actually the pair creation of particle and antiparticle. So when you apply an electric field to the system, then you create virtual pair of electron and positron, which corresponds to the fact that in a medium, if you are applying an electric field, the medium can polarize. So this phenomenon is called the vacuum polarization. And vacuum polarization has been measured. It does have physical impact. And we'll come back and talk about towards the very end of the course, so this is sort of preview of it. But the vacuum polarization has been measured, namely, in the presence of electric field, vacuum does polarize. It does lead to physical effect. Yes, Kay?
I have a question. So now I create a hole in the negative spectrum,
Right.
which is equivalent to creating
A positron.
a positron
Right.
in the positive
Right.
spectrum. Then can I actually show that the math that the creation of the positron cannot lie in the gap?
That's an interesting question. So again, we're dealing with quantum system, right?
Yeah.
And when you talk about the polarization of an atom, when you apply the electric field on an atom, and of course you can talk about this electron gets excited to the next orbital, that's a real excitation. But the polarization you see in, let's say, helium is virtual in a sense that you compute the secondary perturbation, the electron goes up and come back down only within uncertainty principle because it costs you energy. So you are not really exciting the atom, but you are virtually exciting the atom where you can bring the electron up and bring it back down with a delta T, which is less than h over delta E. So you can basically borrow energy to pretend the system gets excited as long as you pay it back within the time allowed by a certain principle. And it turns out that the way you compute the polarization of helium atom corresponds to that virtual effect. And that's what you have done in second order perturbation theory. When you apply the electric field, that's a perturbation to the system. You have the initial state. And second order perturbation is EM. That's a change in energy. You probably have seen this formula, second order perturbation theory. What you're doing is that your perturbation is exciting the system to some intermediate state, like taking the helium with 1s state to 1p state, or 2s state, or 1p state, just momentarily. But you don't observe this 2p state. You need to bring it back to the original 1s state. So this intermediate state is virtual. So the way the helium atom polarizes is because of this virtual phenomenon. You're not really creating an excitation, but you do need an excited state, because you can virtually excite the real state, the virtual excited state, as long as you go back to the original state allowed by the certain principle. So the way the vacuum polarization works in space out there is the same. You cannot create electron-positron pair because that would require delta E of 2mc squared. That's a big gap. But as long as time is less than this, you can virtually create electron-positron pair, and the vacuum polarizes because this electron would shift the opposite direction of the electric field, the other positron shifts to the electric field, so it polarizes just a little bit. So that's a very tiny effect, but nonetheless you get it. But if it actually, electric field is large enough, you can have very interesting phenomena. I was not planning to talk about any of these things, but anyway. If you have strong enough electric field, then this virtual effect can create electron and positron temporarily, and that costs you energy of 2mc squared. And then the electric field would move positron this way, electron this way, and how far they can go is limited by delta T times speed of light, because nothing can go faster than the speed of light. And delta T, we know, is less than h over delta E, and we know this one is 2mc squared. So this is as much as these virtual electron positron can move. But when they move, positron rolls down the potential hill, electron goes up the electric field, which is actually lowering potential energy. So we have a gain in energy, which is E times delta x twice. And 2E electric field, this is delta x. So if electric field is strong enough that this gain in potential energy can overcome the initial energy you borrowed, then this electron positron can become real particle and come out and you can observe. That would require very, very strong electric field, because this has to be negative, which means EE has to be bigger than M2C cubed over H bar. Am I doing this right?
M squared.
Something is wrong.
M squared. And 4
M
E.
squared.
And there's 4 E's. And there's an E in the bottom.
But this is weird. Oh, I see. This right? Okay. And this field is called Schwinger field. So if you manage to create a very, very strong electric field, then what was originally this virtual pair of electron positron by borrowing energy can become real, and you see an avalanche of electron positron production. And nobody has observed this yet, because nobody managed to create this strong electric field, but there are proposals to use powerful electron accelerator and shining that on by the laser. Then the combination of the strong beam of electron and the laser field could in principle exceed this Schwinger field, and you might observe this avalanche of A plus C minus pairs. So virtual particles can become real. And before I ask other questions, this is actually the same thing as the Hawking radiation from a black hole. So when you create two particles, instead of electric field, this could be the gravitational potential. And gravitational potential is given by Gn times the mass of the black hole over the horizon scale squared. And by putting them together, you can work out what is the mass or energy of the object you could in principle produce at the boundary of the black hole at the horizon. And by putting in the solution of the Schwarzschild, the black hole, it doesn't have to be that complicated. All you need to know is the size of the black hole. The horizon scale is 1 over Gn mass of the black hole. And this is the only thing you need to know. And then you can estimate what is the energy you can create real out of this gravitational field near the black hole horizon. And that will give you the estimate of the Hawking temperature, because that will correspond to the mass of the particle you can create. This is actually 1 over Gn mass of the black hole as well, with some combination of H by C, I don't remember, but it's the same physics. Starting with K.
Yes, can you explain the borrowing of energy? Where can I see it in the algebraic kind of missed that part?
So the borrowing energy is originally this one, because you are creating a pair of particles that constitute 2mc squared. So you have to pay that within this delta t. So maximum distance they can move is this delta x, c times delta t.
Yeah.
And then I compare, by letting them move a little bit, can you pay back the energy you borrowed by the gain in potential energy? And that's how you can estimate what the Schwinger field is.
Then I have two questions. First, so now is energy conserved? And the second question will be, so if we have a time that we allow, then it means that it has causality. Which causality?
Causality.
Causality. Okay. Yeah. So we have causality. Then does it give us any? Because if we have causality, it means that we have it before and we have it after.
Yeah, that's right. There is.
Is there anything to do with entropy?
So that's the thing about Hawking radiation, right? So the radiation has entropy,
Yeah.
and that's why black hole has an entropy.
Oh, okay.
So it does. Yes.
Yeah, so I have two questions too. So in the Schwinger field, doesn't that disobey conservation of mass, because you're creating particles out of nothing?
The mass is not conserved. The only thing that's conserved is the energy. Because mass is a type of energy which corresponds to rest energy of the particle.
Okay, the second question was, since you said that vacuum is a Fermi degenerate gas of positron.
Right, that's right.
Then why doesn't that annihilate our matter around us? Because vacuum is everywhere. Why doesn't that annihilate?
Because when it wants to annihilate, you have to put a hole or positron in a state that's already occupied.
Oh.
So it turns out that there's a Fermi blocking.
Okay.
The only way you can really excite energy over 2mc squared, you can annihilate particles.
Got it.
Yes.
So it's
Sarah? No.
Yeah, Sarah. Yeah. It's obvious to me in sort of the electric field example, the electron moves against the gradient for the. It's not obvious to me what are the two things for Hawking radiation.
Yeah, so maybe I should do this a little bit more carefully, okay? So here's a black hole, and here's the horizon. And instead of talking about electron, let's say you create two virtual pair of photons. And that costs you energy, which is twice the mass and energy of the photon. But then, one photon starts to fall into the gravitational potential, the other one tries to escape within the time allowed by h over delta. How much they can move is c times that. Then the gain in gravitational potential is Gn black hole horizon size squared times delta x. And I don't remember H, Y, and C, so let me make all of them to be 1. So the condition is that this is actually gain instead of loss, so that these photons can come to real. So what that means is that E gamma has to be less than Gn black hole horizon size squared. Delta x is this H mod C delta E. Delta is 2E gamma. I move this to this side. So you have this condition. And this Gn black hole, the horizon size is 1 over Gn black hole squared. So this is Gn and black hole cube. No, inverse. I'm doing something wrong.
Isn't the
It's
spiritual
2Gm.
radius is 2Gm over C squared?
Ah,
so
okay.
yeah.
So this is inverse. So then the energy of the photon is limited by this. So that means that you can create excitations only when excitation energy is less than something, which is what basically corresponds to the Hawking temperature. Because you can create excitations up to some energy. It turns out that they are thermally distributed, and that's the idea of the Hawking temperature of a black hole. So that's how you can estimate the Hawking temperature of a black hole without getting into general relativity or anything. The only thing you need to know is the horizon size and quantum mechanics, and then you can work out the Hawking temperature. Does that answer your question?
Yeah, so I guess the idea is that the photons are sort of always going in all directions, but when they meet this condition,
Right.
then we can see them.
Right.
Okay.
Of course, nobody has seen Hawking radiation because the typical Hawking radiation of the astrophysical black hole is so low that you can't even really see any photons coming out of it. But if there is a hypothetical black hole which is much smaller in mass, in principle you could see it. And when the LHC was starting up, there was this hype that you might create a microscopic black hole that might eat our entire planet. That's dangerous. You should stop this experiment. There was a lawsuit and everything, but it did. So we are safe because it is supposed to radiate right away and disappear. Yes.
Oh, I have a question. So we talk about the annihilation of electron, and then if we talk about creating virtual pairs of particles, then I have a question. So we talk about energy, where we create a hole and then annihilate a particle. But so we have the same amount of energy. Why cannot it be like not positron or something else? Like if it's
So in principle, you don't have to use the language hole. You can stick to electrons throughout and talk about this positive electron, positive energy electron that's not occupied, negative energy electron that is occupied, and we can keep using the language too. It's just that it's very inconvenient.
But why can I say, like, I have a electron that is with this amount of energy, and it is equivalent to, say, a neutron with another amount of energy, which is, do I have to preserve that it is still an electron?
Sorry, you said neutron?
Yeah, why can't I change it, you know, because
Because they have different quantum numbers. Neutron has something called a baryon number. Electron has something called a lepton number, in addition to electric charge. So that would allow you to distinguish these different particle degrees.
so this conservation of baryon numbers is actually implied, or
Well, it's empirical. As far as we know, baryon number is conserved because we haven't observed a proton decaying into positron. If it's not conserved, you might say that the proton has charge plus, and the positron has charge plus. Why can't it decay into positron? And nobody has seen that. So that's why empirically, we assign baryon number 1 and 0 for these particles to forbid this decay.
Okay.
But we don't know fundamental reasons why such a number is conserved.
Understood.
Okay? And this is, I think, end of the class, and for you welcome to stick around and ask some questions. I completely went off the track today, but anyway, I thought it was fun too anyway. So I get back to the original track and getting into the next stage of actually superconductivity, where in addition to this free fermion, we spent a lot of time on free fermion today, but when you introduce some weak attractive force among electrons, then this Fermi surface becomes a little bit wide and soft, and then you have a situation like this, which is very much analogous to Bose-Einstein condensate in case of the bosons. You have condensate of fermions. It turns out that's a condensate of pair of fermions, and that is what is called the BCS state, body Cooper-Schwinger, and that's a description of the superconductor. And so I will briefly talk about this sort of analog of Bose-Einstein condensate and fermion systems on next Wednesday, and then move on to the next section of the spontaneous symmetry making. Okay? Any other questions? Good. And I have an office hour as usual. I temporarily forgot the time. That's 3 p.m. Okay, okay. And I also opened the Zoom room for anyone to connect remotely. All right.